Before I do the next talk, I just wanted to give a couple, I thought I should give a couple of bit more overview of what now there's probably have done enough experimentation that these will make sense. A bit of an overview of the Interlagos architecture, which is a bit complicated, but it is relevant, especially when we're going on to look at NUMA stuff, the non-uniform memory access. So the confusing thing is there's a thing on the Interlagos called a module, which is 2 cores, core 0 and core 1. And the special thing about core 0, core 1, 2, and 3 between the odd and even cores is they actually share a floating point unit. And they also share the L2 cache. But the main thing is they share a floating point unit. So it's not clear if these are really 2 cores or... It's sort of like having SMT. It's a bit of a hybrid. So, I mean, for someone who's doing scientific and technical programming, which is floating point intensive, it's not clear whether you really gain anything from these 2 cores. So that these 2 cores are a bit weird. So but the next level is how are these put together into, I'm not exactly sure what the terminology is called, but I'll call it a die. So this is a bit more. So the slightly weird thing is that there's 4 blocks here, okay, corresponding to 4 floating point units. It's slightly weird thing is that there are 2 cores for each floating point unit. But other than that, it's fairly classical. We've got this look like my diagram. We have 4 floating point units, each with an L2 data cache of 2 kilobytes. There's a shared L3 cache. This can actually be shared. It's actually 8. It's 8 megabytes. But unlike the L2 cache, the L3 cache can in principle be used by all of this core. This core here could use all the L3 cache if it was the only one that was operating. But so this is basically what you would have called an SMP on a die. It's a symmetric multiprocessor, but it happens to be put on a single piece of silicon, and it's got 8 cores. But the Interlagos processor on the Cray appears to be a 32-core shared memory system. How does that work? Well, what they do is they bolt 4 of these together. Sorry, that's wrong. That's 8 core. That was my mistake. They bolt 4 of these together to make the 32-core node. And the way it's done is we have 4 of them, and they're bolted together through hypertransport, which is a communications mechanism. But basically, there are 2 of them are stuck together on one piece of silicon. So each what I would call a processor has 16 cores on it, and there are 2 sockets on the processor. So there are 2 16s making 32. But they communicate with each other. Each of these is a genuine little symmetric multiprocessor, but they communicate with each other through these external links. But it is cache coherent across the whole thing. So it's a fully cache coherent system. But the immediate thing you can say is, well, wait a second, this is memory. This CPU, surely it's fast to access this memory, but slow to access this memory, and that's true. That's why it's called a non-uniform memory access system. Basically, to build large systems, the memory, here you've got 8 cores, and the memory doesn't belong to any core, but when you build it up, there's a sense of the memory belonging to a particular bunch of cores. So each bunch of 8 cores has its own home memory, and it has other people's memory, all of which can be accessed in a symmetric shared memory way, but the access speeds are different. It's very fast to access that memory and slow to access this memory. This is what a Cray XE6 node looks like, which is what you're running on. But I'll now give the lecture on NUMA issues. So although non-uniform memory access is only just starting to appear in multi-core processors because people are trying to take them beyond the limits of an SMP, they say, well, I want to do 32 cores, but I can't have uniform memory access across that. There have been NUMA machines for a long time, and Silicon Graphics used to build very large shared memory machines. They still do. The Altics is still going hundreds of cores, and this is how it works. So the main point is that the classics, the Snoopy protocol we had, where everybody monitors all the accesses on the bus, doesn't scale. Both the bus itself and the memory become a bottleneck. So using buses in a single main memory doesn't scale to a large number of processors. So what you do is you try and build a distributed shared memory machine. So it's designed to scale to a large number of processors, but still have the single address space, meaning you can still run threaded programs across them. You can have a single process accessing all the memory. And in fact, these kind of modest-sized multi-socket systems like we're talking about here, maybe a couple of 8 or 16-core processors clipped together, connecting over hypertransport, are actually a facet of, are actually an example of distributed shared memory. And so it's also true of these recent multi-core chips. So one of these Interlagos processors is actually non-uniform memory access. It's 2 blocks of 8 which don't have uniform memory access. But the slides I'm showing are really sort of looking back more historically to how you build very large systems. So what you do is to build distributed shared memory, what you have is you have a bunch of little less symmetric multiprocessors, which are genuine shared memory. Here I've only got 2, a bus and some memory. Then you connect them together with another network, okay? And it's still possible, I don't quite know how the hierarchy works, but it's still possible to have cache coherence between these 2 processors via Snoopy protocol. They both watch what's going on the bus, but it doesn't scale to this larger network. So how are we going to make sure that if this process reads some data from its memory and caches it, that if this process reads the same data and caches it and updates it, that this process knows, okay? We know how to do it if between these processes sharing the same bus, but in this more general architecture, how are we going to do it? And what you do is you take a different philosophy. In the Snoopy protocol, it's the individual core's responsibility to take care of its own. You have to monitor all the memory traffic and make sure you keep your cache up to date, right? So everyone does what they want. All the other cores, you do what you want. The other cores have to monitor it and keep up to date. To build a distributed shared memory machine, you take the other approach. What you do is when you update your cache, you tell everyone you've done it. You broadcast it out, right? You say, right, I've just updated this cache line. Who needs to know about it? So you broadcast it out, and that scales a lot better. So there's no snooping. What you have is a directory structure. So you have for every block in the memory, for every cache block, you have 1 bit per processor, which is set to 1 whenever the corresponding processor caches the block. So what you have is for every block in the memory, say you've got a cache line of 256 bytes, you have a way of knowing through this bit vector which processors have cached that. So the basic idea is whenever somebody takes a copy of a cache line, there's a central repository which remembers who's got copies of the cache lines, okay? So there's a directory you can look up and say who has these cache lines. In the Snoopy-based protocol, you never did that. You didn't care. You just said, look, I've updated this cache line. All you guys, it's up to you to take care of it if you've got it. In the directory-based protocol, if I update a cache line, I go and look at the directory and say who needs to be told about that update, and you tell them about the update. Now this can get quite heavy, because if you've got a 128-byte cache block, right, for those, and you have 256 processors, for each cache block of 128 bytes, you need a bit per processor to remember who's got it. So each 128-byte cache block comes with a 256-bit directory, which is 32 bytes. So actually, of your total memory, 20% of your memory is stored in the directory. So there are limits to this, but I don't know. I have to say I'm not an expert. I don't know what the techniques to get around this are. I don't know if you have hierarchies, or I don't know if you have hierarchical directories of directories. But you can see that the naive approach is going to take up quite a lot of memory. But in principle, it's possible. So as I said, the basic idea is there's a central repository, a directory, which everyone can access, which tells you who has cached a particular cache block. So whenever you update it or access it, you know who to tell. So you have a special home node where the directory entry is located. It has to live somewhere. But you have the same. You have really the same. The principle is the same. You say, for example, have 3 states. modified, shared, and invalid, and the directory entry records that. And what happens is whenever you do something, when you have to update the directory, and you can, for example, invalidate copies in a remote cache or fetch the data back from a remote cache. So basically, if you want some value, rather than broadcasting it over onto the network, onto the bus, you go and look at the directory and say, who's got this value? Who will I get it from? Or if you update a value, you go to that directory and say, who needs to be who needs to be told about this update? So that's the way that it works. So in fact, for the purposes of this lecture, the way that the cache coherency protocol works doesn't really matter, other than you know that it's there. The important point about this diagram is that all memory is not equal. Accessing this memory is quick because it's local. Accessing that memory is slow because you have to go over 2 buses. So you can use these directory-based cache coherency mechanisms to build large shared memory systems, but they have non-uniform memory access, and that's what we're going to investigate. So these systems are called CC-NUMA systems, cache coherent non-uniform memory access systems, and the classic example used to be something like an SGI Origin 2000 or an SGI Altix. As I said, the main problem is that access to remote memories takes longer than to local memory. And so the question is, when you allocate something, where do you put it? In a true shared memory system, it doesn't matter. When you allocate something in memory, it goes into memory. Cores processors may later cache that, okay, but where you allocate it doesn't matter. There's only one piece of memory. In a CC-NUMA system, in a non-uniform memory access system, it's not obviously clear where to allocate memory. And it's the operating system responsible for this. And, you know, what do? I want to allocate 1 gigabyte. So let's look at this picture here. I want to allocate 1 gigabyte array, okay? So this process, you've got a process here that says, I want to allocate a 1 gigabyte array. What do? Do you assume that the process or the thread that's allocating is going to be using it, so you put it all here? Or do you say, no, it's a distributed structure, so you put maybe 1 gigabyte on each of here? Or do you put the first gigabyte there, the second gigabyte there, the third gigabyte there? Or do you sort of round robin on a page basis? It's not obvious how you should allocate these memory. So the standard trick is, well, the most common policy is first touch. You allocate on a node which makes first access to the page. So what you say is, when you do a malloc, you don't actually allocate the data. Okay, it's not actually allocated till it's touched. So what you say is, whoops. Sorry, I wanted to go. I've lost my this picture. What you say is, you allocate, because memory is actually allocated on a page-by-page basis, where the page is well, on a normal system would be a few kilobytes. On HPC systems, it could be megabytes. But there's a quantum of memory which is allocated. So what you do in the first touch policy is you say, if you're the first person to ever access some memory, then it will be allocated on your node. Okay, and that's really good if the first time you ever access memory is the same pattern you're always going to use. Okay, it's kind of self-healing. It means that if the first time, so let's imagine, for example, that we've got an OpenMP loop across a big array, where we've just done a standard block distribution, so the iterations distributed across the threads, you know, the first block here, the second block here. If we have a first touch policy, the first iteration of the loop will be slow because the memory will be allocated, but it will be allocated in exactly the right position. The memory here will be allocated to those threads, to those processes that access that memory. The problem is, often, the first time you use an array, you don't access it in the standard policy. If you zero an array and you zero it all on one thread, you say, I don't want to parallelize that. I'll just have one thread zero the whole array. Then it will be allocated all on here, and then all the accesses will be slow. If you call calloc, which zeros arrays, the same thing. Okay, so it can be quite difficult So you don't have explicit control over where, or you don't have easy explicit control over where memory is accessed, allocated. It's the best thing to do is to make sure the first time you touch it in the same pattern you're going to use. That often maybe means a dummy loop, just put a dummy loop in the right access pattern. It can be a bit difficult to do. But you have to be aware that often the first time you access an array, it might be I/O, for example. You're not actually accessing it in the pattern you're going to use later on. Now you might say, well, surely that's not a problem. If processes or threads access data which isn't in their cache, they get copies of the cache lines. The cache lines migrate. Why can't memory migrate? If the operating system sees that the memory here is being accessed exclusively by the thread over there, why can't it migrate the memory from there to there, just like it migrates cache lines? Well, in principle, you can. It's possible for the operating system to move pages between nodes as an application is running. You can migrate them or replicate them. In practice, this never well, every silicon, in the old days, these silicon graphics machines, they always turned that off because it was a total nightmare. And I don't believe that Linux, can Linux do that? I'm not an operating system person. I don't even know if Linux... But will it do it based on, you want it to do automatically, saying, right, this page is, in the last 5 minutes, this page has been allocated 1,000 times by that process, so I'll migrate it. So yeah, you can do it by hand, but you'd like the operating system to monitor it and do it. So it never really worked. So unfortunately, that's the big problem about NUMA systems. If your data is laid out wrong for the cache, after the first iteration, it'll all be cached in the right place and you're fine. That works itself out. If your data is laid out wrong for NUMA, it never works itself out because it's stuck where it is, okay? So that's the problem. NUMA is a bit like having, well, it's sort of like having cache, but without actually being able to move the data around. It's slightly weird. There are other policies, round robin, but first touch is, I think, the standard default. So as I said, the cache cosignature is maintained in the same way, but each page of memory has a home node, but in practice, they don't migrate. So in cases where the operating system was capable of migrating them, nobody ever allocated it. Nobody ever enabled it. And I don't believe that Linux does it. The current Linux doesn't do it by default. So the exercise is to actually basically, the OpenMP version of the cache OMP code, if you look at it, the first time it touches the array, it does it all on the master thread. There's actually a commented out, you can initialize the array in parallel and get a more NUMA-friendly placement of memory, and you should see a difference in subsequent. All you've done is change how you initialize the array. You initialize it in parallel rather than in serial, but then you should see an improved bandwidth later on. It's not quite as dramatic an effect as I'd have expected, but it does show an effect. A student of ours did a project where he looked at how student from last year, and he looked at NUMA effects. So apologies, I had a crib sheet of where the actually I don't want to view full screen, do I? But he has some nice tests where I'll just get that. So he was looking at the effects of NUMA effects. So the first thing he did was he looked at if you were running fewer cores than your system actually has, how is the performance affected? So what he did is he looked at taking a standard parallelization from the NAS parallel benchmarks, which are available in OpenMP, and just looking on a particular system. If I have 2 cores, and there were 16 cores on this system, if I have 2 cores, what's the worst and the best performance depending on which of the 2 cores from the 16 I pick? And obviously with 16 you've got no choice. Well, you do actually have a choice as to which part of the problem they do. But it's the first order you don't have a choice, you just use all 16. But it's surprisingly big variation of order, 30%, 25% variation. So that shows you on, I think this is on a sun system, that you get quite significant variations depending on where you place the data. The other interesting thing he looked at was, so this, now this is why I was surprised at the exercise I've given you. You do see an effect where you do NUMA aware or non-NUMA aware initialization to get the memory access allocation correct. But what he did is he took the CG benchmark from the NAS parallel benchmarks, and basically the original, has a proper memory allocation. It allocates the memory in a parallel way. But he turned that off and did a serial memory allocation, and he saw that for the NAS parallel benchmarks, he's got a whole bunch of stuff here, but if we look at this here, he was getting a factor of almost 8 between the correct initialization, which was being done, and an incorrect initialization, which is he was getting enormous differences. Here again, factors of 2 or 3. So for the NAS parallel benchmarks, which he didn't modify the code other than the initialization, they have OpenMP versions. He saw NUMA-aware initialization, where you simply initialize the array in the way you're going to use it in parallel, versus a serial all-on-one node allocation, performance differences of factors of 3 or 4. Now, we don't see that in the example I'm giving, but I think it might because we're doing such a simple memory access pattern. We're just doing a streaming access. Here, this does a much more sparse, it's a conjugate gradient, so it does a much more scattered memory access pattern. So I think if you get it wrong there, you have a large number of small transactions, which is exactly what you don't want. But I don't quite understand. The same thing, that was all on an Intel, a Sun, that was all on AMD processors. Saw similar performance on an Intel processor. I could just, he had too much, and that's Multicore. So this is the one criticism of this student's thesis, is he had far too much data. You can see from this. But no. We get the same thing on an Intel processor. He looked at the effect of best versus worst performance, on the Nehalem. Whoops. So this is the similar run on a Nehalem processor, and I think the effects. I think he found the effects were less dramatic than the AMD, but again, you can see that there is a significant NUMA effect that just depending on which 2 cores you choose to pick to run your OpenMP or threaded benchmark on, you get a large variation between best and worst performance. This is duration, so low is good. So I said it's hard to it seems hard to show up those effects with simple just streams like benchmarks, but you do see something. The thing what I noticed most between the 2 different allocations is that in one allocation the performance is very reproducible, and the other one it seems to be very, very non-reproducible. It seems to vary a lot. So I didn't quite understand. I'll be interested to see if other people get the same results. So that's really all I had to say. The exercise which you have is basically to look at the cache, take the cache OMP code and do a cache aware, a NUMA aware initialization. It just involves, I've left the directive in there, it's just uncommenting a directive. And for example, you could look at the extreme case where you run 4 threads on cores 0, 8, 16, and 24. On the Interlagos, cores 0, 8, 16, and 24 are all in different NUMA regions. So you'd expect that a NUMA aware versus a serial data allocation would have a big effect. In practice, I didn't see an enormous effect. Maybe you see it more when you run all 32 cores. Again, you can also look at whether the false sharing exercise gives you different results if the cores are within the same or different NUMA regions. Again, the results there weren't quite what I expected, but these are the kind of things you can play around with. So there's a tool called Liquid, which is basically a set of tools for helping you manage and understand thread placement, and that's maybe worth looking at if you want to play around with issues. I said that student did it himself by doing a Linux system calls and such like, but Liquid would be a much more cleaner way of doing it. So I guess Liquid gives you the same functionality as AP run, but for general systems, in the sense of place this thread there and pin it and such like. Yeah. So that's something you can look at.